Hello, everyone, and thanks for joining today's webinar. My name is Amy Perez with Emphasis Stellagen, and I will be your webinar host today. Before we dive into the presentation, I'm going to cover a little bit of housekeeping. This webinar is being recorded, and an on-demand link will be available and shared with you post-webinar. Please feel free to share the link with your colleagues. You can submit any questions you may have in the Q&A box in the lower right-hand corner. We will spend some time at the end of the webinar to answer your questions. If we do not get to your questions during the webinar today, we are happy to follow up via email. And last but not least, if you are on Twitter or LinkedIn, be sure to follow Stellagen for news, resources, and announcements for future webinars. Today, joining us, we have Dante Martinez, Senior Solutions Architect. Dante is an AWS Certified Solutions Architect with more than 20 years of experience building software delivery and operation systems. He brings a true mastery of the DevOps and SRE frameworks, resulting in solutions that lead product development and operations teams to the highest success levels. Dante is a part of an all-star team that architects and develops solutions to accelerate, secure, and modernize software delivery and operation. Also joining us is Jeff Montgomery, Sales Director. Jeff has over 30 years in the software industry with experiences ranging from software engineering to running a multinational cybersecurity consulting services organization. Jeff's experiences over the last few years have been focused on cloud adoption as an AWS practice manager and now responsible for Emphasis Stellagen DevSecOps and DataOps practices in Eastern and Central US. At this time, I'd like to pass the mic over to Jeff Montgomery. Hi, Jeff.
Thank you, Amy. Appreciate that. I'm going to spend a few minutes introducing Stellagen, and then we'll get into the meat of the discussion. Stellagen's been around for about 10 years, a little over 10 years, focusing primarily in DevOps, DevSecOps, and now more recently DataOps as that has become more popular. We pride ourselves on the fact that every engineer within our organization has at least one and more often multiple AWS certifications. We have a really great track record with our customers. We're showing orders of magnitude in accelerating their development processes in the cloud, specifically in AWS. We have a good track record of being thought leaders in this space. Our founder, Paul Duvall, has written a number of books and authored a number of blogs who you can find out on the web if you search for his name. Really putting a lot of edgy thoughts in the market and pushing people to drive DevOps to the next level. In that time, we've seen a trend where the benefits that you can leverage in DevOps for applications is starting to become applied to data as well. And we're going to spend some time on that. Next slide, Dante. So generally speaking, we have the philosophy across the entire company of automate everything, right? So as I mentioned before, the trend of showing, things that people have specialized in applications, DevOps and applications and getting features into the apps more quickly. You have an idea in the morning and it's in production that day, right? That's what people want to get to. And primarily over the last several years, it's been around applications, but there's no reason why those same concepts can't apply to data as well. Data has a similar type of life cycle. Machine learning models have a similar type of life cycle. Why can't you also gain that benefit of automation in the data life cycle as well? So again, our view of automate everything has been the genesis of some of our thought-leading initiatives around DataOps as well, which is what Dante is going to spend some time with you today. Dante?
All right, so thank you, Amy and Jeff, and good day, everyone. So yes, as Amy mentioned, and Jeff mentioned, I've been helping organizations build software delivery and operation systems for several years now. So my dad was actually an industrial engineer. He spent most of his life increasing the efficiency of manufacturing facilities, particularly denim plants. So if you're wearing a pair of jeans at an affordable price today, you have him to thank for it. So I grew up visiting a lot of those factories and from time to time, and came to appreciate the work that went into continuously improving how product was made. And that's translated into my desire to help organizations produce new software and applications. DevOps and in turn DataOps borrow concepts and frameworks originally developed for those manufacturing processes. So automation of software production came quite naturally to me. So today we're focusing on the data side of the equation, and in particular, we'll take a look at how automation in the form of DataOps is an enabler of cloud-based modern data architectures. But first, let's take a moment to contrast a modern approach to a classic, but still very common architecture. So this is a bit simplistic, but we're simply showing how in a classic data architecture, your focus is on monolithic database or stores. In this example, we've got 4 applications that all interact with a single shared database. Then you've also got a single shared analytics database. In between, we've got a limited set of pipes to move and prepare the data for analytics. Now, this setup works just fine. In fact, millions of companies are still running on designs like this. It can be difficult to make the decision to move away from this type of architecture because it's tested and true. And more than likely, your companies have invested a great deal of time and money building out that infrastructure, developing ETL processes, stored procedures, and analytics, all based on these single sources of data. So what I see a lot of companies do first is they look for a cloud equivalent to replace that single monolithic database. That can definitely be done. You can definitely lift and shift your entire data architecture as is into the cloud, but it's often disappointing because you end up with the same problems related to the use of that monolithic architecture. Now, just as with monolithic applications, the biggest drawback is that you create a tight coupling between your database and every application service, ETL process, or report that interacts with your single data set. This means that any changes to that data set or the infrastructure running that database, you've got to coordinate that with everyone involved. This slows production down as you must now test your changes against dozens or hundreds of interactions. The next drawback is that scaling and performance become incredibly difficult as your data sets grow large. Now, cloud has made the resource scaling issue trivial, but it is still challenging to scale ever-growing monolithic data sets. Improving application performance becomes difficult. So imagine, if you will, a single shared database, which over time ends up with rather large tables. That can make data retrieval difficult since you must join multiple large tables to fetch the required data. And speaking of constraints, you're more likely stuck using a relational database for your monolith, meaning that all your applications are also constrained to using that same type of database. That leaves you unable to take advantage of NoSQL or other lighter weight options for your applications and services. And lastly, the monolithic database makes finding and accessing data difficult as it grows. We've all been asked, where's my data? Which usually kicks off a time-consuming process of finding specific data sets, describing the use, and making them accessible for consumers. All of these problems add up to assembly line bogging down in terms of data development and consumptions. My dad would be pretty disappointed in this model. So if there's one thing I want you to take away from this brief comparison, it's that there's a price to pay in staying with this type of architecture. In terms of long, slow development cycles, which equate to long, slow, and expensive business decision cycles, while your competition leaves you behind. All right, so what's an alternative approach? Again, this is a bit simplistic, but we're showing here what those same 4 applications might look like in a modern data architecture. Here you see each application or service has its own database or store. Each application owns its data set independently of each other, meaning you can make changes to that data set without concern of disrupting another application. You're no longer constrained to using a single type of database either. So go ahead, use NoSQL, GraphSQL, flat files, whatever's best for your particular application or service. You're now free to deploy any given service and data set or changes to those independently of all your other services. This also means you can scale easily by simply scaling these smaller discrete database or store on demand. Good performance from an application standpoint is also easier to achieve as you no longer must deal with joining or moving large sets of data that are irrelevant to any particular application. Now, another way to visualize this is to see your application and data set stacks, how they map to your business domains and have bounded context based on those business requirements. This is a code first versus a data first approach, where your business requirements drive the code design first, and then that code design drives your database design. Now, the neatest thing about this service is when that consumer comes asking once again, where's my data? Now, instead of an arduous search followed by an urgent operation to make it available, I can simply point them to a directory of data sets, each of which is discrete and self-describing and was defined by a business domain. In fact, done properly, you'll never hear this question again because those business domain stakeholders would have been involved in defining and deploying those data sets from day one. Now, two key principles of designing a modern data architecture. First, database or data stores are discrete and belong to their assigned application or microservice. They are essentially private, so the inventory service can't access or modify data in the shipping service and vice versa. The great thing about this is if I want to make a change to my inventory service, I don't need to involve my shipping service team to do that. I'm free to innovate and iterate on this service as the business requirements demand. I can scale my inventory service database on demand without worrying about the state of my shipping service. Providing access, securing, and monitoring my inventory dataset is also greatly simplified because only the inventory service needs access to that dataset directly. Now, our applications and services do need to interact still, so we do this utilizing an event-driven architecture. In this model, you provide loose coupling between application and datasets by utilizing message queues and a pub/sub event-driven data flow. Instead of waiting on a resource-intense ACID transaction, you make your applications more available and performant by offloading events to a queue via messages. Your application can define and self-describe the events it publishes independently of the subscribers. In fact, your application won't even be aware of the subscribers or what they do with those messages. It's this loose coupling between components of your architecture that enables you to build highly scalable and distributed systems. Now, we're used to thinking of the pub/sub model in terms of application events, but there's no requirement for an application or service to be involved here. Most cloud-native database or data stores have the ability to send messages based on data-driven events. This means that you can trigger actions based on data lifecycle events, allowing you to orchestrate data flow independently of the application as well. Okay, so a quick overview of a few other characteristics of a modern data architecture. First, it's very adaptable. In a modern data architecture, data flows like water from source systems to business users. The purpose of the architecture is to now orchestrate that flow by creating a series of interconnected data pipelines that serve business needs. Those pipelines are constructed using base data objects, so data snapshots, data increments, data views, reference data, master data, and flat subject-oriented tables. The data objects serve as building blocks that are continuously reused, repurposed, and replenished to ensure the steady flow of high-quality, relevant data to the business. Now it's a collaborative endeavor. Unlike the past where the IT department built everything, a modern data architecture shares responsibility for acquiring and transforming data between IT and the business. Data engineers and analysts in business units use data preparation and data catalog tools to create custom data sets composed of corporate and local data and provide them for use by business unit applications. The modern data architecture is also smart. This goes beyond automation and includes the use of machine learning and artificial intelligence to build the data objects, tables, views, and models that keep data flowing. It uses intelligence rather than brute force to identify data types, common keys, and join paths, identify and fix data quality errors or map tables, and identify relationships and recommend related data sets in analytics. A modern data architecture uses intelligence to learn, adjust, alert, and recommend, making people who administer and use the environment more efficient and effective. Finally, a modern data architecture bakes governance and security right into the data sets, workflows, and pipelines. It does this by making each component responsible for its own security and governance. Dataset self-describes, by means of metadata, who has access and under what conditions or forms the data can be shared. A pipeline must respect those conditions as it moves data from one location to another. So, for example, a dataset that originates in Europe might be tagged as GDPR compliant, and a pipeline would be prohibited from moving that data outside of the EU region. A dataset that originated with private medical information might be tagged as HIPAA compliant, and would not provide access to applications or users outside of that defined consent boundary. Additionally, each dataset is tagged and self-describes its lifecycle information. Each object has an owner, location, and an obsolescence plan, for example. Okay, so now we've got an idea of what a modern data architecture looks like now. My father never got into software development, but I like to think he'd appreciate the efficiencies gained with this approach and the incredible value to businesses that utilize it. Now, there's always a catch, right? And this is where we start to see the requirements for automation and the DataOps framework in order to successfully build and operate a modern data architecture. So with any distributed architecture, the primary trade-off is that you now have many more objects to manage independently. In terms of provisioning for each application, you may now have dozens or potentially hundreds of independent databases, stores, or objects. Each of these objects has a life cycle that must be managed. Each of these objects must be provisioned, configured, operated, and monitored. What's more, you must now orchestrate a large number of data streams and movements. In the classical architecture, this was limited to a handful of movements from large database to another large database. Now, each and every data set may interact with every other data set, leading to an exponential increase in the paths that data may travel. And all those nodes you've now deployed also need to be secured and governed. More endpoints equals more ways to infiltrate. You must define and manage access, use, network, and store controls for many more objects now, and you must monitor for secure interactions on a much larger set of data flows. Finally, all of these areas, provisioning, orchestration, and security, are defined in code. Infrastructure is defined in code. The pipelines to deploy that infrastructure are defined in code. The data sets that are now self-describing all come with metadata, which is code. The pipelines and step functions that define the movement of data are defined in code. Data operations like ETL, conditioning, preparation, etc., all of that defined in code. Security, use, and access, all metadata code attached to the data sets. And the orchestration of everything I've talked about, all of this is defined in code. Code is everywhere, and you must now manage the creation and iteration of that code as well. All of these new management requirements can sound overwhelming at first, but with the right approach, this overhead can be automated and operations can be efficiently conducted. That's the goal of the DataOps framework. All right, so let's start with the textbook definition so we can get that out of the way. DataOps is a framework of technologies and practices for building, operating, and managing data pipelines from source to consumption. Now, DataOps is a subset of the DevOps movement in the software engineering world. DevOps bridges the traditional gap between software development, QA, and operations so technical teams can repeatedly deliver high-quality systems at an ever-increasing pace with no loss of stability or governance. Like DevOps, DataOps shares responsibility for operation with all stakeholders, which on the data side of the coin means data architects, data engineers, data scientists, data analysts, application developers, and IT operations collaborate to deliver on the organization's need for data. DataOps borrows heavily from Agile, Lean, DevOps, and total quality management from the manufacturing world. Similar to Agile, DataOps emphasizes the use of small development teams with business involvement and short, typically 2 to 3 week development sprints that deliver fully tested, production-ready components and code. Similar to Lean, DataOps focuses on efficiency using version control systems and code repositories that foster parallel development and code reuse. And like total quality management, DataOps focuses on continuous automated testing and monitoring to detect issues before or immediately upon promotion to production. Now, from a business point of view, DataOps takes in business requirements for data on the left and outputs business value in the form of data that can be used for guidance with business decisions. Now we'll look at the framework from the data lifecycle point of view. From this perspective, DataOps takes in raw data sources on the left and outputs refined data ready for consumption on the right. The processes involved in the lifecycle are defined by business domains, codified, and then implemented by operations teams. Each of these steps in the data lifecycle has tooling and automation that can be leveraged to reduce the overhead and management time required. This, in turn, improves the cycle time to value of your data. Okay, so what does it take to implement DataOps? We'll now take a look at the 4 epics to build out and apply the DataOps framework in your organization. All right, so epic 1, as I mentioned before, everything is code now. To extract value from data, your progress through a series of steps. Data must be conditioned, validated, transformed, combined, modeled, moved, analyzed, and reported. Conceptually, the pipelines used for these stages are implemented using a variety of data tooling, including ETL, data science tools, self-service data prep tools, reporting tools, visualization tools, and more. These stages are then executed by a pipeline in a deterministic fashion defined by scripts, source code, and algorithms, config files, parameter files, and even containers. All of these items are code. So code controls the entire data pipeline from end to end in a reproducible fashion. The artifacts that make this reproducibility possible are also subject to continuous improvement. So just like other software projects, the source files associated with the data pipeline should be maintained in a version control system such as Git. A version control tool helps teams organize and manage the changes and revisions to code. And it also helps keep code in a known repository and facilitate disaster recovery when needed. However, the most important benefit of version control relates to a process change that it facilitates. It allows data team members to branch and merge. So in a typical software project, developers are continuously updating various source code files. And if a developer wants to work on a feature, he or she pulls a copy of all relevant code from the version control tool and starts to develop changes on a discrete copy called a branch. This approach can help data teams manage changes to the data pipeline in parallel. When changes to a branch are complete and tested, the code from the branch is merged back into the trunk where the code came from. Branching and merging can be a major productivity boost for data teams because it allows teams to make changes to the same source code files in parallel without slowing each other down. Each individual team member has control of his or her own work environment. They can then run their own tests, make changes, take risks, and experiment. If they wish, they can discard their changes and start completely over. This leads us to the next capability you will need to build for a DataOps implementation. Allowing team members to work well in parallel relates to providing them with an isolated environment where they can deploy those branches. So in Epic 2, building on the DataOps framework, you see each data team member has their own development tools in their own work environments. Version control tools allow team members to work on their own private copy of the source code while still staying coordinated with the rest of the team. For most data development, a team member can't be productive unless they also have a copy of the data, or at the very least, a subset or representative set of that data. So if everyone tried to work from a single source, conflicts would occur. A database engineer changing a schema may break reports. A data scientist developing a new model might get confused as new data flows in the middle of its testing. So providing discrete environments to each team member isolates the rest of the organization from being impacted by their work. Here we can see how version control, branching and merging, and multiple discrete environments work together. Note that each environment was provisioned from the same configuration template, so at startup, they're exactly identical. Each, however, will execute a different branch or version of the code, and this allows you to isolate environmental factors from issues with your executing code. For data development, the environment consists of the defined data set and the operational resource that runs your application, transform, model, or other service that interacts with the data set. Ideally, that operational resource is in the form of a containerized package of code. Once the code is placed in a container, it's much easier to use by other programmers who may not be familiar with the custom tools inside of the container, but know how to use the container's external interfaces. It also simplifies deployment of that code into each environment. Now, in most cases, your workflows are going to need the capability to incorporate different runtime conditions as well. So which version of a raw data set should be used? Is this data directed to a particular environment? Or should a particular filter, say a PII filter, be applied to the data on ingestion? Or should a particular set of processing steps in the pipeline be applied or not? A good pipeline design will allow the engineer to invoke those options by utilizing parameters instead of writing a completely new workflow. A parameter is simply a flag passed by the pipeline that affects the way it operates. So imagine, if you will, An engineer has just created a new data model and would like to test it independently with data sets from 2 different regions. So in this case, the engineer can simply pass the America parameter to load the data set from the Americas in this first run. And on the second run, they can pass the Europe parameter to the same pipeline and load the data set from Europe. This ability to pass in parameters into your pipeline allows your engineers to work in defined environments, but still maintain the flexibility to develop and test with different runtime conditions or different data sets. Okay, so what does provisioning an environment look like? Here we can see an example of an analytics environment with 3 components defined. So an input data source, a data transform, and the analytics code itself to generate reports or other refined data. All of this is declared in code, in this case, a YAML template. The engineer created this template, and the pipeline provisions the required infrastructure and configuration based on that template. But now we can also iterate on this configuration as needed. Let's say we need to add a new data source. The engineer can simply modify the template to add the new source. The pipeline then provisions the environment into a temporary testing area, executes a series of validation checks, and then, assuming everything checks out, provisions the environment into a work state area. All right, so one last takeaway on environments. Those templates that define the environment are immutable. That is, each and every time the pipeline reads a specific template, it will provision the exact same environment. It doesn't matter if that environment will be used for testing a new feature, fixing a bug, or deploying your final production code. The environment will operate exactly the same in each use. This allows you to independently test your code without worrying about issues with the environment runtime conditions. All right, so we'll take a bit of a tangent on our DataOps journey, but security is often defined together with the environment itself. And in the DataOps framework, security definitions are baked into each data object, and the pipeline is the application and enforcement mechanism. So a layered set of controls is typically used to ensure that requirements are met. The first of those layers is the preventative control, used typically to validate a data object or resource is configured correctly before deployment. The next layer will utilize the same control definition, but will monitor for violations after deployment and also continuously in any running environments. This is known as the detective control, and it will flag and notify of any runtime violations. The last layer, a reactive control, will take any output from the detective control and trigger an event that can remediate or take further actions to mitigate or correct the violation. All right, so let's take a closer look at how those controls work in the context of a DataOps pipeline. So here we have an example of a preventative control. Our engineer has attempted to deploy a data store without encryption. You can see there encryption equals false. The pipeline will execute a static analysis of that configuration template, and upon seeing the violation of the requirement for encryption, it stops before deployment and generates an error for the engineer. The engineer can now correct the configuration to include encryption, and the pipeline will provision the store this time. Take note that the preventative control is applied before provisioning. Next, we move further up the pipeline, and for the detective and reactive controls, these are enforced post-provisioning, and they both monitor operating environments continuously. Note that these controls will use the same control definition or rules as the preventative control, but will poll the operating environment regularly to check for violations. So here we have the same control requirement that any data store must be encrypted. Our engineers provisioned an unencrypted data store out of band from the usual process. That provisioning process generates an event message to our operations management system, which detects a violation of the rule and triggers a notification after flagging the data store as non-compliant. At this point, no further action is taken, but the same event message can be passed to a reactive control. Again, the same control definition is used, but in this case, it triggers a remediation function which accesses the cloud provider's API and actively changes the configuration of the data store to add encryption. Okay, so in these examples, we've shown a security control, but I want you to understand that these controls can be used for governance and operations purposes as well. Any configuration of a data object can be managed with these controls, in fact. So you need to ensure that a particular data set doesn't leave its local region. Use a preventative control. Do you need to ensure that PII data is removed before relocating a data set? Use a reactive control to trigger a filter process. Okay, so back to our DataOps journey here, and the next critical piece to build out on this journey, Epic 3, is your testing capability. So if you make a change to a data object or a process, how do you know that you didn't break anything? Automated testing can validate changes without time-consuming or manual testing. This ensures that releases are high quality before entering the operating environments. So the idea in DataOps is that every time a data team member makes a change, they add a test for that change, the equivalent of a unit test. Over time, the testing harness is added to incrementally with the addition of each feature, so testing gradually improves and quality levels also increase. These processes are baked right into your pipelines. These testing harnesses are analogous to the statistical process control that is implemented in a manufacturing operations flow. Tests ensure the integrity of the final output by verifying that work in progress matches the expectations. And testing can be applied to data sets, models, and logic. For every step of the data pipeline, there should be at least one test. Start with simple tests and grow over time. Even a simple test will catch an error before it is released out to the users. So for example, just making sure that row counts are consistent throughout the process can be a very powerful test. One could easily make a mistake on a join and make a cross product which fails to execute correctly. A simple row count test would quickly catch that error. And tests aren't limited to errors either, right? Warnings or informational events can be triggered when data exceeds certain boundaries. So for example, the number of orders in a week may be okay if it is within 75% of its historical average. If the order levels are above or below that threshold, then that data set could be flagged for investigation prior to being further processed. So keep in mind, DataOps is not about being perfect. In fact, the framework acknowledges that the development process is imperfect. Testing ensures that you can determine the cause of any issues quickly so that you can correct it earlier in the workflow. And they can also add new tests to ensure that those same errors don't happen again and again. And this will continuously improve the quality of your development efforts. Now, with a suite of tests in place, DataOps allows you to move fast because you can make changes and quickly rerun the test suite. If the changes pass the test, then the data team member can be confident and release it. The knowledge is built into the system and the process stays under control. Tests catch potential errors and warnings before they are released, so the quality remains high. All right, so let's take a closer look at how you can incorporate testing inside of a data pipeline. So here we see a set of stages for an ETL testing pipeline. Now, ETL environments can be pretty complicated configuration, requiring storage location, data sets, ETL application itself, and the actual job code to be defined. But as we saw earlier, the DataOps framework makes the provisioning process of an environment easy by defining all of that in code and making repeated deployments trivial. So with that in mind, the testing pipeline can deploy an entire ETL environment on demand whenever new ETL code needs to be tested. The testing pipeline provisions the environment, then executes a series of tests automatically. In this case, we're testing data quality by checking for correct formatting and reference values. We then test the transform itself by comparing output to expected output. And finally, we test against business rules to ensure that none were invalidated in the transform process. The pipeline provides immediate feedback on any errors or warnings from the test to the developers, so they can then iterate on the transform code if needed. Or if the tests all pass successfully, the pipeline continues and can deploy the environment to higher level testing stages or into production. All right, so on to our final epic of the DataOps journey, building out your pipelines. So in the DataOps framework, there are two categories of pipelines or workflows that you will build. The first type, the data pipeline, will prepare and condition data for consumption. Here you see raw data enters the pipeline from the left and moves into production processing. Production is generally a set of stages, so access, transformed models, or streams and filtering. And when data exits the pipeline in the form of refined data, value is created for the business. The data sets in these types of pipelines are updated on a continuous basis, but the process code itself is kept constant. Now, the worst thing that can happen in this type of pipeline is that poor quality data enters. So the DataOps framework prevents this by implementing data tests and preventative controls. This ensures that input data values lay within an acceptable quality parameters, and data tests validate the data values of both the inputs and outputs of each processing stage in the pipeline. So for example, it'll check input on a zip code should be 5 digits, and output of a complete address should include a zip code as part of that address. Now, these tests work continuously to guarantee the integrity of your data pipelines and workflows. Quality is built in and integral to the entire system. So if bad data flows through the pipeline, the data test will flag this and take corrective actions, like by notifying a team member or even stopping the line before the low quality data impacts higher stage processes. Your data developers and engineers can now focus on innovating the code that extracts value from your data. All right, so let's take a look at an example of a type of data pipeline. This one is related to orchestration processes around streams. So here we have 3 different paths of log data generated by an application. So on input, test validate that formatting and values are acceptable before streaming to a new storage location. The pipeline then provisions and executes the data stream for each of these paths. Each of these streams is codified with a set of instructions on processing the data as it moves. And here our API event logs need some filtering before moving to an alerting mechanism. Our application logs need some enrichment by joining to another data source showing IP addresses, for example. And our instance logs need aggregating as there are many instances running for this application. This data pipeline prescribes and then orchestrates each of these paths and the stages of data flow. The other type of DataOps pipeline is the code pipeline. And in this type, the data set is now static, and the new data operations code is executed against those static data sets. So the goal of this type of pipeline is to implement new ideas that extract value from the data. Here we can see that just like application code, a new idea or feature undergoes development before being deployed to a production system. In fact, these types of pipelines are analogous to the DevOps-based CI/CD pipelines for applications. All of those are designed to facilitate the development of functional code. And key to this is a fast feedback loop so that developers get frequent feedback on errors or issues with their code. Okay, so during the development of new features, code changes, but data is kept constant. Keeping data static prevents changes in data from being attributed to the new code. So remember, your environment provisioning pipeline makes this trivial now and can deploy environments with static data and code versions passed in as parameters. DataOps implements continuous deployment of new ideas by automating the workflow. It reduces the overall cycle time of turning ideas into innovation. And the DataOps framework uses logic tests to validate new code before it is deployed. Logic tests ensure that data matches business assumptions. So for example, a field that identifies a customer should match an existing entry in a customer dimension table. A mismatch should trigger some type of follow-up with logic tests in place. The code pipeline can be automated for continuous deployment, simplifying the release of new enhancements and enabling the data team to focus on the next valuable feature. So with the DataOps framework, the dev team can deploy without worrying about breaking the production systems. This is a key characteristic of a fulfilled productive team. Okay, now in the last steps of our journey, we combine the data and code pipelines. And in the real world, these pipelines are not separate. The same team is often responsible for both. The same assets are leveraged, and events in one affect the other. The two workflows are showed combined here. This joint pipeline captures the interplay between development and production and between data and code. So DataOps breaks down this barrier so that cycle time, quality, and creativity can all be improved. The DataOps enterprise masters the orchestration of data to production and the deployment of new features, both while maintaining impeccable quality. Reduced cycle time enables DataOps engineers to impact their organization in highly visible ways. Improved quality enables the team to move forward with confidence. And DataOps speeds the extraction of value from data and improves the velocity of new development while ensuring the quality of data and code in production systems. All right, so our journey completed. We can take a look at what a successful DataOps implementation buys you, right? So DataOps can accelerate the ability of data teams to extract value from data. It requires an agile mindset and must also be supported by an automated platform, which incorporates existing tools into a DataOps development pipeline, as we covered today. A well-designed data pipeline can serve as a competitive advantage for data-driven organizations. So here we see how features of the DataOps framework provide valuable benefits to your business. The framework allows higher development throughput, which leads to the higher efficiencies and lower costs. The collaborative model of DataOps, coupled with continuous monitoring of operations, provides the capability to scale on demand and builds reliability right into the system. And the test-driven operations model ensures quality from data source to data consumption. Finally, the automation as part of the DataOps framework leads to shorter cycle times and, key to your competitive advantage, faster time to value for your data. All right, so I hope you've enjoyed this overview of DataOps today, how it can help you achieve a modern data architecture. And I hope you enjoyed the tour of the 4 epics that will enable you to build out a DataOps platform for your organization. Before we wrap up, we will be answering some of your questions, so get those into the chat window at this time. And okay, now, so I'll hand it back over to Jeff, who's got a special invite for all of you. Jeff?
Hey, great job. Fantastic insights. I think certainly since we first started talking about this idea of DataOps, 2 or 3 years ago, it's matured quite a bit, and we're seeing a ton of activity. And one of the things that we're learning in those actions is that while Dante takes you through all of these examples, everybody's circumstances are a little bit different. So what we offer folks is to come in and spend some time firsthand looking at your environment, understanding what your requirements are. DataOps requirements for someone who's starting something new is different from someone who maybe has a mature DevOps environment and wants to take some of those practices over. It really depends on what it is you're trying to get to. There's also aspects of making sure that you're constantly evaluating what you're doing and understanding and analyzing over time, how are things actually working. And, we have practices in helping people handle that type of situation. And all of those objectives and all those requirements are understood through this workshop approach, coming in, spending some time with you, listening to you, hearing what your requirements are, what your priorities are, and putting together the best plan going forward for you. And you can ask us to help you with that plan, or you can take it on yourself, whatever you want. So I would encourage you to take a look at what we offer in the way of a workshop. Encourage you to take a look at what we offer in the way of an assessment if you have an existing deployment. I would give you one hint: take a look at something called Topograph. We've got a really cool assessment engagement powered by some IP that we've come up with that embraces some machine learning, that goes out and really takes a look at your environment to give you some strong insights, and it helps drive some of the workshop and other type of planning activities that will engage with you. The workshop itself is on us. It's something we come in and try to help you with. So again, please go out to our website, which I think you'll see pop up here in a few minutes, and ask us to come by and take a look and have a conversation and plan your next steps in your DataOps journey.
Wonderful. Thank you so much, Jeff, for that. And thank you, Dante, for all of that information. And thank you guys today for attending. We hope that you can take the lessons learned today and begin your journey to a modern data architecture powered by DataOps. If you're interested in learning more about the DataOps workshop that Jeff just mentioned here, more information will be provided to you in our follow-up email, which will also include an on-demand link to this webinar. You can also reach out to sales@stellagen.com if you have any other questions. As we wait for questions to come in right now, I want to take this time and remind you that questions can be posted in the Q&A box in the lower right-hand corner. Additionally, please feel free to visit our website at www.stellagen.com for blogs, case studies, and more information around offered services, including DataOps and Topograph, which Jeff just mentioned. I did receive a couple of questions here that are being sent to me. So Dante, if you're ready, we can go ahead and get started. First question that I have here, can you talk about some of the tooling used in DataOps?
Yeah, absolutely. So the tooling is similar to what you might use in the DevOps realm. It's probably not quite as developed, and there's definitely a lack of centralized DataOps specific tooling. So in most cases, if you're doing this all natively, let's say inside of AWS, you might use your typical pipeline tool in there. So you could use Code Pipeline, for example. But in most cases, Code Pipeline is just too application centric. And there's also a lot of functionalities when you're working in the data side that take much longer periods of time to complete than on the application side. And they oftentimes require a lot more validation as well. So on the AWS side, typically you will end up using step functions far more frequently to build out those workflows than code pipelines. Now there are some DataOps specific tooling that's fairly recent additions. There's an open source tool called Apache Airflow, and there's also a couple of managed services. One I'm familiar with called Upsolver. So I've got seen excellent experiences with all these, but they're geared typically around orchestrating data movement, managing the ability of those data sets to self-describe, and automating all of those processes. But the nice thing is all of those can be incorporated or integrated with your existing pipeline tools as well.
Thank you for that, Dante. Another question I have here is, what support for legacy data tooling is available?
Okay, so yeah, so surprisingly, it's not as difficult to integrate a lot of the legacy tooling as you might imagine. Even in cases where those legacy tooling are not cloud native, they may offer an API into the tooling, which you can integrate with step functions or your pipeline tools. And even if they don't, if they just provide the ability to work from a command line, we can often times script that automation and integrate that with the pipeline as well. So the biggest issue we see with a lot of the legacy tooling is that they don't offer yet a way to codify either configurations or the whatever transform or conditioning or prep they're doing for that code. So that's a challenge there. Now the good news is, or the ability here is that when you do start to move to more cloud native technologies, those ability to manage all of that in code becomes available to you.
Thank you. And another question we have here is, how do you transition from a monolithic data architecture to a modern data architecture?
Sure. So, the process is similar to breaking up a monolithic application, right? So you want to start by laying out your business domains and let those business domains drive the process for you, right? So oftentimes you may have a required function or feature derived from that business domain that will drive the design of the application or the service. And then that in turn drives the design of your database. Now that's a little backwards than most data people are used to working with, right? In a typical monolithic situation, you're often designing the database schema ahead of time, and then the application has to adapt to that or use that. But in the microservices model or in the DataOps framework, that process is driven strictly by the business domain side of things.
Thank you. And then just one more question here. You had touched on what the core skills are needed to gain a data ops role, such as Python, SQL, and Git. Are there any other core skills that you feel like is necessary in order to gain a data ops role?
Yeah, so just a good understanding of automation and how to build those efficiencies. The tooling is very specific to your data tooling, right? So it's hard for me to say, if you want to work in DataOps, go learn this particular skill set. You're going to just have to learn each and every one of the data tools there. But conceptually, learning how to build automation and learning some of the same principles that you would learn in DevOps, right? So, for example, just understanding that when you're building a pipeline out, you generally want to have quick tests to the left of the pipeline, as you will, so that you catch simpler checks or simpler tests earlier in the pipeline and provide feedback faster. And then more expensive tests and more expensive checks of your data sets go to the right side of the pipeline. And those will be run less frequently than the quick checks will. So having a good understanding of those DevOps principles will definitely go far on the DataOps side as well.
All righty, thank you. I believe that concludes the rest of the Q&A. Dante and Jeff, thank you both so much for your time today, and thank you everyone for attending. Again, just a couple of reminders. The on-demand link will be headed your way in a follow-up email along with information around the data workshop. Please feel free to share this with your colleagues as well. With that being said, have a great rest of the week, everyone.